Hey, I'm Key, and on this playlist, I'll be teaching physics. First of all, you'll need some pretty good understanding of linear algebra and algebra 1 and 2, with trigonometry, logarithms, and other functions that would be necessary. Later along the line, you're going to need beginner calculus, like calculus 1 and 2 with derivatives and integrals, and even later along the line, you're going to need calculus 3, partial derivatives, and differential equations, as well as partial differential equations. Now, let's start with vectors. I'm going to draw a Cartesian plane here. Now, in physics, you don't write a number to represent the values in a Cartesian plane. You rather put plus x and plus y, unknown x and y values, and the origin being equal to 0. Now, when we draw a vector here, this x is a function of time because x changes with time. And y here is also a function of time because it changes with time. Now, these two are related by one variable, making them a parametric function. Now, if you don't understand parametric functions, Ryan will talk about that later on in his playlist. And now this vector over here. Now this vector over here, since it is a vector, must have a magnitude, which is length, as well as a direction, which is this angle theta over here. Now a scalar, however, is just a numerical value or a value. So a scalar would be like the length of a ruler, 12 inches, or the temperature of a room, like 30 degrees Celsius. A scalar does not have a direction, but to make it have a direction, we could say this ruler of 12 inches is pointing upwards. Now, this ruler is pointing upwards, giving it a direction and a magnitude, making it a vector. Forces are also vectors. For example, when I have this person over here, pulling a very heavy object of 1,000 pounds. Now, over here, this would be a vector because it is pointing in a direction. The rope has a force applied to it, which is a magnitude. Now, this would also be a vector, its magnitude being the velocity of the stick figure and its direction being to the left, which means 0 degrees in direction. Now, a vector field and a scalar field, a vector field would have many different sizes of arrows. Going this way. Just imagine that at the end of each line, there will be an arrowhead. This is not very well drawn, but you get the idea. All of these vectors create a vector field. These vector fields can be seen in real-life situations such as wind maps, where they tell you the direction and speed of the wind. But scalar fields, however, would have different colors representing different temperatures. The temperatures do not have a direction, so they are not a vector, hence scalar field. Another example of a vector would be gravity. Now the gravity is an arrow pointing down, magnitude being 9.8 meters per second. This value doesn't really matter right now, but we will use it later on for projectile motion equations as well as free fall equations and other extremely important concepts that we will learn later on in this course. Now, since this is a direction and it has a magnitude, this would be a vector. Now, we will learn how to represent vectors as unit vectors. Let me draw a Cartesian plane over here. again, plus x plus y. Now, let me draw another arbitrary vector. Magnitude being 5. We will call this vector m with the arrow on top, because whenever we have a vector, the letter with the arrow on top means vector m. Now, a magnitude is just the length of the vector in this situation. The magnitude of a vector can be denoted by vector m with an absolute value sign on top. So in this situation, this would be equal to 5. Now, when we represent a vector with a unit vector, we must understand that adding vectors is taking a vector, for example, here and here, taking the tip of the first vector and the tail of the other and putting it on, creating this. And since, assuming this is the origin, the new vector would be this. It's the tip of the vector over there. So now let's understand here, this is a Pythagorean triple for convenience. Now 3 and 4. This angle over here, direction, and a 90-degree angle, because it is a Cartesian plane. Now, this is a vector magnitude 3 and a vector magnitude 4. Now, this vector m is equivalent to this vector plus this vector, because when you put the tip of this to the top of this, when we draw it, it becomes vector m. Now, a unit vector, as you can infer by the name, is a vector of magnitude 1, point in a set direction. Now, this vector over here we would denote as I hat, and this as j hat, is the standard way to denote a unit vector in mathematics and physics. Now, a j hat vector pretty much means a vector with magnitude 1 pointing up, and an I hat vector being a magnitude 1 vector pointing right. Now, when we put a negative sign in front of these, it just flips the direction by 180 degrees. So it would be negative j hat, and this would be negative I hat. But we don't need to worry much about that right now. How can we represent these using I hat and j hat? Now, 3 to the right. Since I hat is 1 to the right, this would be equal to 3 times I hat. Because since this has a magnitude of 1 and is pointing to the right, any vector with a magnitude of 1 pointing to the right would be the same as I hat. So even though one vector can be here, if it's the same magnitude over here, they are the same vector. Now 4 over here can be denoted by 4 times j hat, because it's 4 times a unit vector going up. Now, why does this make sense, you might ask? Well, in vector notation, you denote this as the tip of the vector x and y over here. Now, in here, a unit vector would be, for I hat, would be 1, 0, means the tip of the vector is 1 over here, but 0 in y, which means a unit vector over here. Now, j hat would be the opposite, 0, 1. Now, j hat over here means 1 in the y direction and 0 in the x direction, hence j hat in the up direction of a magnitude of 1. We are pretty much multiplying both the x and y component, so we are going like here, multiply 3 by 1 and 3 by 0, which becomes 0, but this time this becomes the vector 3, 0, and over here this should be 4. 4, you distribute it into the 0 and the 1, this becomes 0, 4. So now when we add these together, the 3 adds 0 becomes 3, and the 4 plus 0 becomes 4. The tip of the vector would be 3 comma 4, which would be the tip of this vector. Now, this notation would be extremely useful in situations where we're calculating instantaneous acceleration as well as instantaneous velocity in both 1 dimensions, 2 dimensions, and 3 dimensions, and many more. Thank you for watching.